Oh, it captures the screen. Yeah, no problem. Hell, I'm the only one here. All right. Fuck it. You know what I'll do is I think I'll just write over here. We can all see this, yeah? Okay, cool. So can this. And you know, if I don't capture it, come to class. All righty. Let's see if I can do anything more helpful than this. There we go. Probably we'll do that. And I think this overlays. So we should be cool. All right, what questions did you have for me? I didn't see anything filled out. So we all get resting membrane potential pretty well?
I have a question about slide 32. The one about the space constant.
Space constant, gotcha.
Just if you could.
Something like this?
Yes.
Okay.
Can you just go to that slide again?
Yeah, sure.
Thank you.
So right now we're just thinking about passive movement and charge. We'll get into active movement later. No, not that. And then we'll mix up passive and active when we get to the dendrites. So this is just about passive movement. If we bring charge in and we let it spread out, how far does it go? That's what the space constant asks. It's going to go a whole lot further in real life when we have active conductances, because as we move on to the next bit of membrane, we're going to open up ion channels. So we'll refresh it. But if we just were to inject current, we had no active conductances going on, and we let that charge spread, that's what lambda is giving us. And that's going to be a function of how easy is it to escape versus how easy is it to move within. That's it. So if you want to increase passive propagation of charge over distance, you need to either increase your membrane resistance so charge can't leak out. So when we're thinking of the membrane circuit here, the resistors, maybe this. Okay, so the resistors are the what? What do we think of when we think of resistors? Thank you. Yeah, ion channels. So when they're closed, very high resistance, and when they open up, resistance drops and we get current. So you could get rid of ion channels. Neurons do this. In some sections of the axon, they'll get rid of ion channels. That's going to increase membrane resistance. So we're not going to get as much leak. The other thing you could do is decrease your internal resistance. So what creates internal resistance? You ever use a hose? Cool. Me too. So you turn the hose on. Water comes out. If you want that water to spray further, what do? You've already turned it up all the way over here.
You like, you know.
You put your thumb on it.
Yeah.
Yeah, exactly. You're going to increase internal resistance is what you're doing.
Yeah.
So you're going to get a stronger current because you have the same potential. You have the same amount of water coming out. So you get a better current whenever you increase your, well, you get stronger current shooting out. As a result of that, you're going to need a stronger current. So when you put your thumb over the hole, you're decreasing the diameter. So So you could make a wider axon, and that would have lower internal resistance, but we don't do that. Why not?
The signal would propagate much slower.
We could, yeah, for sure. We have a little more capacitance. That would suck. It kind of defeats the purpose. Why else don't we increase the diameter of our axons? Yeah, space. Exactly. Because we have a skull. So you increase the diameter of the axon, well, you can't pack as much stuff in there. So all the space constant is telling us is how far can that charge spread before it's decayed by about 63%. And that's going to be a function of how easy is it to leave versus how easy is it to move. Make sense? That's really all you need to know there. Neurons don't have to worry about that so much whenever they have active conductances to propagate. Any other questions?
Can we go over the quiz?
Yeah, sure.
All ion questions.
Yeah.
Okay, sure. Yeah.
How many of the questions were potassium?
I don't know. What were the questions?
Which ion has biggest impact on resting membrane?
Okay, that seems like a reasonable question to ask for the lecture on resting membrane potential.
Correct.
Okay, something like that.
Yes.
This one doesn't have answers. I can tell them to you, but I'd like to see what you've picked. Because if you got them all right, we don't need to dwell on it now, do we? Let's see. There we go. Okay. Jam that in there. Responses. All righty. Have I told you all that you shouldn't pick the longest answer, and you probably shouldn't just pick all of the above just because I write it on there? Yeah, I know. And I know that, so I write it. They don't all have the biggest impact. Only one of them is going to have the biggest impact, and it's potassium. How did you know that it was potassium?
I wrote down has greatest permeability and strong chemical gradient.
There you go. Has greatest permeability. So the resting membrane potential is going to be largely determined by what's going on with potassium. You might be tempted to pick chloride, but no one did. Why would I think you'd be tempted to pick chloride? There you go. Yeah. Yeah. Common mistake. It's not the case here. All righty. So we're going to assume membrane potential of minus 70. What is driving force? There you go. So what's our membrane potential right now? True. Wasn't ready for you, but yeah. And then where does the ion want the membrane potential to be? So how far are we from that ion's reversal potential? So here's the variable that we'll plug in. You'll take the absolute value here. So the further you are away from that ion's reversal, the greater the driving force. In other words, the greater the effect opening an ion channel is going to have. So if you're already at reversal, it doesn't matter if you open any more ion channels. You have nowhere to go. You can't get any closer to the reversal if you're already there. The further you are away, the greater the net flux of ions. So if we're at reversal, let's think about this for just a second. Which ion do you want to think about? I can't hear you all at once.
Potassium?
Oh, fine, let's talk about potassium. I don't know which one you want. You have to tell me. What's the reversal for potassium? Oops. What's the reversal for potassium?
-1 and 2.
Just ballpark. Yeah, there you go. Pretty negative, right? I'll just call it 100. Let's say that we patch a cell and we take it on down to minus 100 and we don't kill it. So we'll set our VM equal to minus 100 millivolts. How much driving force is there? Thank you. Subtract something from itself, you get 0. There's no driving force. So let's say we open up some potassium channels. Is potassium going to move across the membrane? Yes. Yes, it is. I was trying to trip you up a little bit right there. Don't think that just because you don't have a driving force that there's no movement of ions. How does the movement look like? Let's say here's our membrane. Here's an ion channel. We open up our potassium channel. That's what this is here. Here's potassium on both sides of the membrane. We'll put a whole lot more of it inside. Hopefully that makes good sense to you. It does to me. We're at reversal though. Okay, we got our patch pipette over here, and we've set VM equal to minus 100 millivolts. Does potassium move in? You've already told me it moves across the membrane. Yes, it'll move in. Will it move out? Yes, it'll move out. How do these rates compare to each other?
It likes to move out more.
At reversal? No, no net flux. They are moving, but there's no net movement. It's going to kind of wander in. It'll wander out, same rate. So you won't detect a current, but ions are still moving. Keep that in mind. Ions are always moving. At reversal, we don't have no ion movement. We have no net movement. Ions are always moving in both directions, even when you're not at reversal. What we're measuring is the net movement. Ions are just kind of moving chaotically. They're going to tend to move in a certain direction because of those two forces, the diffusive and the electrical force. But it's still chaos. They're moving every direction. Okay, so back to this. We're at minus 70, and I got to give you the membrane potential if we want to figure out driving force, because that's what's going to determine driving force. We have to know where we are right now. Maybe we're at rest, minus 70. Maybe we've adjusted it. Maybe we're depolarized a little bit because of excitatory input. That's going to affect driving force. But right now we're at minus 70. Okay, we already know it's calcium because it's green and has a check mark next to it. What's the reversal for calcium? Why is this correct? Great, positive 125, and this will be in millivolts. How about chloride? Rough ballparks here. Nice. Pretty close to rest. That's what we should be thinking of here. Calcium, really, really positive. Chloride, pretty much rest. Chloride currents are going to tend to hold us near resting membrane potential. How about sodium? Great, positive 50 something. Yeah, whatever. So very positive still. How about potassium? Yeah, somewhere in the ballpark of minus 100. So hyperpolarizing. So for chloride, just think it's pretty close to rest. Sodium, depolarizing. Potassium, hyperpolarizing. The action potential makes a whole lot more sense if you know these two things. And this, really, really depolarizing. So now what we have to ask is how far are these values from minus 70? This is 195 millivolts away. This is 6 millivolts away. This is 126 millivolts away. This is 30 millivolts away. 195 is the biggest of those numbers. So that's the greatest driving force. This is a great reason why calcium is used as a secondary messenger. It has such a strong driving force, even during the peak of an action potential. Even if you get all the way up to positive 30 millivolts, you're still going to get a net influx of calcium. It's a great secondary messenger for that reason. It also has very low intracellular levels. That's what gives rise to this very depolarized reversal. Do you all know the equation that we're going to use to find these values? Thank you. Boy, I hope so. You should know that by now. The Nernst equation is pretty handy. You should know it somewhere in the back of your head. Now, of course, on the exam, you can look up anything. And one of the things that you have to look at would be this calculator here. We're going to take a look at this together to make sure we know how it works and what everything means. And we'll answer a few questions using it. Yes?
Yeah, it's broken.
How?
We're sorry, this document is not published.
Huh? Well, it's a liar.
Yeah, it says you need access. And then
Oh.
it gives me this thing.
Hey, hold on now, hold on.
Yeah, you may need to make it.
Anyone with link, try it.
Okay.
Refresh that thing.
Yep, we're good now.
Okay, thank you. On occasion, roughly daily, I'm going to make mistakes. So don't be afraid to let me know. So if you find something like that, I've told you there's a spreadsheet and you go to it and it's not working for you, just send me an email. Say, hey man, will you fix this thing? That's the issue. Okay, so yeah, we'll look at this together. What are we on? Which one? Okay, leak. So there are many different types of leak channels out there. That's why we are permeable to sodium, chloride, and potassium at rest. What's the greatest component of our leak current? In other words, which ion are we most permeable to at rest? That's all this is asking. Yeah, exactly. Potassium. So we got a bunch of different channels out there, but today is really all about potassium. Your resting membrane potential is determined largely by potassium. That's why it's very important to regulate potassium levels. When these change, and sometimes they do, that affects the excitability of neurons. If you have hyperkalemia, so a buildup of potassium, for example, your neurons become hyperexcitable. This can lead to epileptiform activity, so seizures. Because your neurons are going to all reach threshold potential at the same time, and that's what a seizure is. A bunch of neurons firing at the same time. Let's see. Okay, so this is all about the space constant. We want to increase the distance over which charge can passively propagate, and that is defined as lambda, which is the ratio of what to what? What's on the top? Rm. What does this M mean? What does the R mean? Excellent. What's on the bottom? Excellent. What's the I? Good. So when you think about a cross section of some sort of neurite, whether there's a dendrite or axon, doesn't really matter. So we slice through it. We're looking down the middle. This is what determines the internal resistance and what determines the membrane resistance. What's that? Yeah, sure. What's stuff in the membrane? That certainly affects it. What I'm looking for, ion channels. How many channels do you have in there? If we have no channels, we're going to have really, really high resistance or really, really low resistance. Yeah, really high resistance. How in the hell is an ion going to move through a membrane if there's no channel for it? It's not. Okay, so what do we want to do here? Which one of these should we increase? Excellent. Membrane resistance. You increase your resistance, you cut down on how much charge just leaks out the membrane. If it leaks out the membrane, it can't move within the cell. That should make fairly intuitive sense. Yes?
So just to clarify, if you increase the diameter,
Yes. Yes. Think of it like a road. How many lanes do you have? If you only have one lane, you're likely to encounter traffic. You're not going to move as far. All right, that's the quiz. Any other questions?
Oh, I think I have one quick. Okay,
All good? Okay, cool. Is everyone else all good? Because now's a great time to ask questions. Okay, well, why don't we run a few then? Oh, Jesus. Why don't we run through a few then? Just to make sure we got the main points. All right. So we have some ion imbalance. I want to make sure that we have in our heads which ones are going to be higher outside and which ones should we be thinking of as higher inside. Nice softball question for you. So outside the cell, what are we thinking about? Sodium. What else? Okay, good. Sodium chloride, calcium. Think of sodium chloride together. Why? Yeah, sure. Yeah. Yeah, but why am I saying sodium chloride? Thank you. Yes, salt water. Where did life begin? Yeah, probably. I would imagine. Probably somewhere where it was wet. And that wetness was probably salty. Yeah, so life began in salt water. So the external environment has always been salt water. Why are we throwing calcium outside? Why? Huh. Phosphates. Yeah, calcium phosphate. This thing will precipitate out of solution at physiological concentrations. When I say precipitate out of solution, of course, I mean it forms crystals. Crystals can be sharp. Membranes don't like sharp things. So we don't want calcium to build up, and we don't let it. We have buffers for calcium. Do we know any of our calcium buffers? What are the things that we put calcium in inside the cell? I'm asking you to remember something from basic biology. Oh, shit. You didn't think you'd ever have to know that stuff, right? The mitochondria is the powerhouse of the cell. What else is it? Big sack of calcium. It's one of the things that we'll use to buffer calcium. You might have also heard of smooth ER. This is the one that gets all the ladies. It also gets all the calcium. So this is going to buffer calcium levels. Has some calcium pumps. It's going to bring it in. This is a really nice source to get a burst of calcium and then suck it all back in without letting it go to waste outside. So we're going to keep calcium levels low. We're going to have a couple sacks of calcium within the cell, mitochondria, smooth ER. Now, if we try to put too much calcium in here, the cell dies. So the mitochondria is the powerhouse, calcium buffer, and the self-destruct switch for the cell. More on that in lecture 15. So that only leaves us with potassium. I like bananas. I eat bananas. Potassium goes inside. I don't know how you want to remember it. You could just knock off all the others and say, well, something has to be inside to make sure that we have relatively equal amounts of stuff dissolved. If we have different amounts of stuff, we have different amounts of water. And that can be bad. Okay, we already had this one. Alrighty, we have differences in their resting membrane potential here. Neuron 1, for some reason, is sitting at minus 65. That's not minus 70. And this one's at minus 75. That's not minus 70. Did I just make this up, or can neurons possibly have different resting membrane potentials? Yes, they can. Why? Why might they be different? But why do they? You're putting the cart before the horse here. You know, I think these different resting potentials are going to determine their firing, but it's your answer is on the right track for sure. What determines the firing patterns of neurons? Have you already watched lecture 3? We'll get there. What do you think it is? To that could be one, yeah, or sodium, or any of these, yeah. What determines our permeability to ions? Thank you, ion channels, yeah. So different ion channels. Maybe they have different ion channels. Well, shit, what would explain that? Why would one be more depolarized? What could cause a depolarized resting membrane potential? Would it have to be more or less permeable to sodium? Comparing neuron 1 to 2, which one do you think might be more permeable to sodium? Why do you say that? This is closer to positive 50 or so than this, exactly. This is closer to sodium's reversal. So maybe this one has a higher persistent sodium current. Maybe this one's lower. How about potassium? Might there be differences in their potassium conductances? How would they compare? Which one do you think might have the greater permeability to potassium? Neuron 1 or neuron 2? Why do you say that? Is it just that simple that when you're permeable to an ion, the membrane potential moves toward its reversal? Yes. Yes, it is just that simple. There are many ways where we could have this difference. It could be because of differences in persistent sodium. It could be because of differences in their potassium conductance. Maybe chloride, but probably not. We can also have differences in calcium permeability as well. That's a possibility. Some neurons use calcium to excite themselves. So there are many ways that you could do this. There's no one right answer here. But you should understand how all of these play together. Which equation are you thinking of right now when you're comparing these and thinking about membrane potential? It's not Nernst, but it's a bunch of them stuck together. Yeah, exactly. Goldman Hodgkin cats. Because you're trying to think about more than one ion at a time. They all are going to play a role. If you increase sodium, you'll depolarize. Or if you decrease potassium, you'll depolarize. Do the opposite, get the opposite.
So the basic principle behind that is sodium is closer to the ion reversibility and increased permeability. Is that correct?
Yeah, exactly. Increase permeability to an ion, move toward its reversal. Decrease permeability, move away. Yeah. Yeah. All righty. Any questions over this stuff? Cool. Okay. We still got stuff. So when we're thinking about the movement of ions, we're thinking about channels. We're not thinking about carriers. We're definitely not thinking about pumps. They're way too slow. For every one ion a pump moves, channels move 1,000,000 of them. Channels are what's going to generate our currents. You can measure transporter currents. It's really, it's kind of difficult because they're small, but you can do it. Channels, real easy. All right. So when we're thinking about ion channels, we can think about a few different parts. What are the parts that we need to have an ion channel? Okay, what goes on in the pore? You got it. So when you think pore, what are you thinking? Yes, that's what it is. It's a hole for ions to move through. And we need that because of the hydrophobic center. Ions won't move through, so we make a hole for them. Now, how do we know which ions are going to move through? All right, and what creates that? What part of the ion channel determines the ion that moves through? So when we're thinking gates, we're thinking opening and closing. We're not thinking about how specific we are or whether or not we filter out certain ions. Okay, that's part of it. Absolutely. Size will matter, and what's going to determine the size? The selectivity filter. That's what we call that part. I'm trying to lead you there, but that's all right. The selectivity filter. That's what we call the part of the ion core that's going to actually interact with the ion or the sphere of hydration around that ion, so the water molecules as well. That's how we can be specific to potassium, but not sodium, even though potassium is much bigger than sodium. If it was just size, you can never have just a potassium channel. Okay, so we got an ion pore, we got a selectivity filter, so we can let ions move through and we can determine which ones come through and which ones don't. Now we have a leak channel. That's all you need for a leak channel. It's always open. Now I like to think of the neuron as a fence. And here's where you can get across the fence. Now we don't jump the fence. Makes the top bar sag, lowers property values. We don't do that. We go through, thank you, we go through a gate. So when we talk about the gating of ion channels, what we mean is what's going to control whether it allows ions to move through the fence. Gates control what moves through the fence. What kind of gates do we have? Activation and inactivation, and they are exactly what they sound like. Activation will determine whether the pore opens or closes. So open the gate or close it. Inactivation gate is going to block it, like picking up the drawbridge or something like that. Doesn't matter if you open the door, it's blocked. Maybe it's more like a bouncer. And this is the velvet rope. I mean, you could get through that velvet rope, right? Not the bouncer. So inactivation is not the same as deactivation. Closing is not the same thing as blocking. More on that next lecture. We should know the difference between all of these. If we activate the channel, we open it. So what happens when we deactivate it? Thank you, we close it. We don't block it until we inactivate it. So what happens when we de-inactivate it? We unblock it. So sure, now if you open it up, ions can move. Alrighty, reversal potentials are big. You need to understand those. What is a reversal potential? Yes, they are the exact same thing. What are they?
It's a certain potential where there's not a difference. Is that where there's no net difference in the ion switch? I don't know what the word for that is. Flow, yeah.
Exactly. No net movement of ions. Don't flow in, don't flow out. And why are they moving at equal rates in and out?
Because it's the same concentration on both sides.
Oh, that could, no. But you're on the right track. Something is canceling out. Now, do we think of our diffusive force as ever changing? I don't. There's a couple reasons why I don't. you're really only moving ions right there next to the membrane, but the bulk of the cell is away from it. So you're not really moving the majority of your ions. You're moving a percent. Now, over time, this would add up. You're clearly moving ions. You are changing the concentration, but it's a very small amount and it's very local. And we fix it. How do we fix it? What's that? Well, we do it with pumps. All right, we're going to move them back. Exactly. That's sodium potassium pump. We let ions move down their concentration gradient, and we move them back. That's why we're spending a whole bunch of ATP. 20%, 25%, something like that. Not a small amount. The sodium potassium pump and other pumps are going to keep ion imbalance relatively constant. So we're not moving that many ions, to be honest, and we're always pumping them back. We should think of the diffusive force as constant. If the diffusive force wasn't constant, our reversal potentials would change. And we'd never know how ions are going to act. It'd be chaos. Everything would reverse at 0 millivolts. Nothing would hyperpolarize. It wouldn't work. So we think of diffusive force as constant. Because think about it. That diffusion difference is what creates your reversal potential. What's the Nernst equation? If you take a look at that, all it's based on is ion concentrations. If these change, this changes. Good thing these don't. This way we can tell, or we can predict, what is an ion going to do. So at the reversal potential, it's not that we have equal concentrations. That diffusive force is constant. And for potassium, the diffusive force is going to push us out. So why do we have no net flux? I have a force pushing out. Something offsetting this. What's offsetting it, Meredith? Oh, there you go. Electrical force. Trying to bring potassium in. So what kind of charge must I have if I'm trying to pull potassium in? A negative charge. And it should be a fairly strong one because I have a fairly strong diffusive force pushing it out. And hey, look at that. It's fairly negative. It works. So the diffusive force, we have no net flux, not because of an equal concentration, but there's no net force. Concentration difference is exactly the same, but what's changed is the membrane potential and thus the electrical force acting on that ion. So there's no net force, no net flux. But one of those forces is constant. This one is the one that's not because neurons play with their membrane potential. It's okay to do that, it's healthy. Let's think about then, we're at -70. What are these ions going to do? Which way do they want to move? Are they going to go into the cell or out of the cell? And by doing that, what are they going to do to the membrane potential? We should be able to know all of this because we know the reversal potential and we know where we're at. We're at -70. Who wants to tell me about potassium? Haley, keep it down. I want to know which way is it going to move, into the cell or out? Why do you think that? Nice. Okay, and we're at -70. What membrane potential does potassium want us to be at? Yeah, excellent. Yeah, so it's going to leave. And when it leaves, what happens to the membrane potential? Exactly. Yes, we're going to hyperpolarize and we're going to approach potassium's reversal. Who wants to tell me about sodium? It's going to go in. Why do you say that? Yeah, here's where we want to be. We're not there. It's got to go in. How about chloride? It's going to go out. Okay, what's it going to do to the membrane potential? Well, we have negative charge leaving. Ah, I knew you were. That's pretty good, Joe. Tell that at the next party you're at while you're social distancing. No, it's not going to leave. It's going to go in. And you knew it was going to go in because you saw this. You saw the answer right there. We want to be negative. You got to bring negative charge in for that to happen. How about calcium? Heard a grunt. We're halfway there. Yes, in. But we're definitely not there. We will never get there. Okay. So what's leak channel? What is that? What do you think of when you hear leak? Yeah, always open. Just always letting the ions move through the membrane all the time. What about a ligand-gated ion channel? What does that sound like? Great. What opens it? You got it. It's exactly what it sounds like. Can you give me an example of a ligand that might open a ligand-gated ion channel? Well, a hormone most likely is going to cross the membrane and interact with transcription factors to adjust gene expression. Maybe there's some cases where it doesn't, I don't know. But hormones tend to be membrane soluble. There are glucose transporters, and they do use some ion conductors. They're not channels. We're getting there. And you're going to kick yourself when you hear the answer. But don't be so hard on yourself. It's okay. Have you heard of glutamate, GABA, glycine, dopamine, neurotransmitters? Yeah, exactly. This would be a neurotransmitter receptor. A ligand is just a thing that binds to a receptor. One of those things might be neurotransmitters. Hormone was a pretty darn good guess, but I think mostly they're going to cross the membrane and act on gene expression. They do also act on metabotropic receptors. And those will eventually affect ion channels, but they're not ligand gated. You know what? I'll say you're probably not totally wrong on that one, but let's just keep it simple. Glutamate, GABA, glycine, your typical neurotransmitters. So these leak channels are all about rest, and ligand-gated ion channels are all about changing us away from rest based on input. How about a voltage-gated ion channel? You ever heard of those? Good. What determines whether they open? Thank you. It's exactly what it sounds like. Change membrane potential, change their gate. Maybe they open when you depolarize. Maybe they open when you hyperpolarize. Those exist. They're really nifty. So whenever we're thinking about membrane potential, resting membrane potential that is, why should we only think about leak? Yes?
Because potassium, because it's the most permeable, so it's the one that's always going to be leak.
All righty. Yeah.
I mean, I said that.
These are all good. Why shouldn't we think about a ligand-gated ion channel? Let's rule the others out. I like what you said. Let's just complete the thought a little bit. Why shouldn't we think about ligand-gated ion channels if we're at rest? Do you feel like you're at rest right now?
Never.
Why aren't you at rest right now? Okay. Well, that's not the time to talk about it. But that probably contributes to it. But you're in class. Why isn't this the time to rest? Oh, yeah. Yeah, I'm saying shit. And you're listening to it. Because on occasion I'll say something true. And you want to write it down. You're receiving input. You're not passive. You're not really resting. If you're receiving input, you're not really resting. So these are going to take us away from rest. What about voltage-gated ion channels? Why shouldn't we think about those?
Because they're not constantly moving.
There you go. Yeah. If you're going to activate them, you got to change the membrane potential. If you're changing the membrane potential, you're doing something. So the only time you're doing nothing is when you're actually doing nothing. We don't have to think about gates. Gates require something to open them, and that's doing stuff. It's all about leak. And these will come up again later whenever we think about synaptic currents and potentials. Because the leak is always there, and it always pulls us toward rest. And that resting potential is not any of an individual ion's reversal potential, but some combination of them based on which equation? Thank you, the GHK. And that's why these values are going to make sense. You've seen these before. What is the P in all of these? Thank you. I'm a pretty simple guy. Don't think too hard, because I don't. So we're resting at about minus 73.4. Based on the typical values for ions inside and outside the cell, and that textbook value of 1 for potassium permeability, about 0.04 for sodium, and about 0.45 for chloride. And what I want you to do is think about what happens whenever we decrease and increase these tenfold. That's what we're going to do in each of these cases. That's why I wanted to make sure this sheet worked. Because I could just tell it to you. But what's the point in that? Can you all find this sheet? I'm on the second page there. The first one is really just this, without calculating the whole membrane potential. So we got a few different moving parts that we can think about whenever we're trying to consider what is the membrane potential going to be. And really, you know what, I don't like this. Sorry. Okay, so 4 ions to think about. We're going to consider calcium as being 0 for permeability. We're basically not moving calcium at rest. All right, we're going to move that whenever we're active. But the others were permeable too. Some neurons will not have a 0 here, but we're in the world of the ideal textbook neuron. So we can change permeability. And what I've done is make it so that you can press this and it'll tell you what the default value is. So what do you want to set it to? What would you like to put our permeability to potassium as? 0.1. Let's take it down tenfold. All right. Now down here, what we're looking at would be the reversal potential for potassium, the current value, and the original value. So this is what it should be for potassium, sodium, chloride, and calcium. You can see the reversal potentials. When we change the permeability, we've done nothing to change the reversal potential. And all neurons are going to do is change their permeability. They're not actually changing external concentrations. That's going to happen more in pathological conditions or in the lab. What happened to the membrane potential? Thank you. Thank you. Yeah, it's just that simple. Don't overthink it. Did we move toward or away from potassium's reversal? Away from it. Of course, we decrease permeability. That's how it works. What do you think happens whenever we increase permeability? Yeah, exactly. It's just that simple. Plug in a 10 instead of a 1, you hyperpolarize. Nothing to it. So notice the reversal potentials haven't changed. This is just your Nernst equation. This Goldman-Hodgkin-Katz equation. Nothing to it. And this is available for you to use as you see fit. You can make a copy, and then you have your own. You're welcome. Now, of course, we could also affect membrane potential if we change these. So sometimes external potassium builds up, and look at that, you're pretty close to threshold potential. You have seizures. Okay, but these are fairly constant. So you probably won't play with these unless you get a question that asks you to. So we can predict what's going to happen because we know if we increase permeability, we're going to move toward that ion's reversal, and if we decrease, we're going to move away. And then we can actually just calculate what it should be using this sheet if you'd like. So these numbers here will make total sense to you. You'll get the same thing. What I want us to notice here is how big of an effect do these ions have on membrane potential? Which one of the ions had the least effect on membrane potential whenever we increased or decreased permeability tenfold? Thank you. Chloride has the least effect on membrane potential. So when you think about inhibitory neurotransmission, which is going to be mediated by chloride currents, these fast inhibition, we're not thinking about profound hyperpolarization. It's all about shunting inhibition. Not a big change. If you see marked hyperpolarization, it's going to be caused by potassium. Chloride just keeps us near rest. That's all it does. Inhibition is not about hyperpolarization. It's about staying near rest. Okay, last little bit here. Let's think about those passive properties of the membrane. And what we need to think about is, of course, resistance and capacitance. That's what the membrane is. We have a battery. That's going to be our sodium-potassium pump. That's going to establish the potentials that then move through the resistors to create currents and get stored at the capacitor. The capacitor is, of course, the lipid bilayer, and the resistors are the ion channels. That's one way of thinking of the membrane. All right, so first of all, what is capacitance? Because we all know what capacitance is. Storage of, thank you, storage of charge. If you're going to store charge, it helps if you don't let charge move through you. You can't store it if it's moving through you. And it also helps if you allow those charges to interact with each other so that their forces will hold them there. The positive and the negative on the two sides will be attracted to one another and less likely to run away. The membrane is an excellent capacitor because it's very, very, very thin and has that hydrophobic core. So, great capacitance. Let's think about the relationship between capacitance and the rate of membrane potential change. So what I want you to try to imagine is, what is this going to look like? Just roughly. I don't have any units here. I want a general idea. If we're going from low to high capacitance, is that going to increase or decrease the rate of potential change? The decreases have it. Yeah. Why do you say that? What did you think about to come to that answer? What's that? Thank you. Yeah, tau. In this case, we're talking about the space constant. We could be talking about a microtubule-associated protein, but we're not. We're talking about the space constant. What is tau? How do we calculate tau? Yes, exactly. And this is all about the membrane. So how long does it take to change the membrane potential by about 60 That's what tau is. It takes a whole lot longer if you have higher resistance because you're not moving charge across it to actually change the potential. And it takes a lot longer if you have high capacitance because you have more membrane to charge before you can actually move and change the potential. Hopefully we remember we have that capacitance current immediately, and then we get our resistance current that actually changes the membrane potential as we can read it. So when we increase capacitance, tau increases. And as a result, we should see some sort of drop. I doubt it's linear, but that's the basic relationship there. Speaking of tau, which one of these neurons is going to have the greater tau? Assume equal resistance. Why do you say that? Thank you. And that's true. The dendrites are going to contribute to the capacitance of the neuron. If you remove all of the dendrites, so if you were to patch onto a neuron and then either pull the cell body out of the slice or take some forceps and pinch very carefully, you would decrease the capacitance of that neuron. Most of the capacitance is actually going to be in the dendrites because that's where most of the membrane is. Increase the number of dendrites, increase capacitance. As a result, this neuron is going to be less responsive to high frequency input than this one over here. All right. I think we've gone through this, but someone just remind me, how is lambda going to be affected by the diameter? First of all, let's define it. That's ugly. Even worse. How do we calculate this? Nice. Okay, diameter. Which one is that going to affect? Yes. That's going to determine your internal resistance. So let's say that we decrease our diameter. What happens to lambda? What's that? Okay, great. So what happens to the internal resistance when you drop the diameter?
When you drop the diameter.
You're decreasing the diameter. Yeah, so let's compare here to here. Which one do you think has higher internal resistance? Great. Much higher internal resistance.
So it's minus higher.
There you go. Decrease the diameter, increase the resistance, decrease lambda. And what does that mean if we decrease lambda? Thank you. That charge will not propagate as far from the source passively. So we're going to need some active conductances to move that along further, if that's the case.
If you want it to propagate further, you have to increase the diameter.
That's one option. Yeah, you could do that. And so that's how invertebrates are going to help solve this problem. What we're going to do is massively increase the membrane resistance through myelination. And the other thing you can do to help propagate that charge is actively propagate it. Put in some voltage-gated ion channels, which we're not going to think about today because it's all about rest. We're resting today. Tomorrow we'll be active. When does this class end? Okay, cool. That's my spiel. Are there any questions? You think you could calculate reversal potentials just fine?
I mean, after this hit really good.
Okay, good. Calculate. Let's make sure. Before we get out of here, let's just make sure. Can somebody tell me what the reversal potential for chloride will be? Let's say we increase the internal to 70 millimolar.
Okay, well, I can't alter the sheet. So
Yes, so now what do you do? I don't want you altering my sheet.
Actually do the math, I guess.
No, never do the math. Never do the math. What are you thinking? You can copy. Yeah. And then you have your own you can use forever. Yes. Still true. Try it out. Make sure you can use this. You might have to. You might wake up in the middle of the night in a cold sweat. Shit.
What did you want us to change it to?
Change it to 70 internal.
How long did it take you to do this?
Couple minutes.
You said which one changes?
Chloride.
To 70.
Yes, and before you say anything, make a prediction. Which way is it going to move? We're right now at minus 76. Are we going to increase or decrease our diffusive force if we bump this up to 70?
How do you say chloride did?
Huh? What's that?
I thought you said chloride did.
True. Just don't, did you jump ahead?
Maybe.
Did you already plug numbers in?
No, I didn't.
Okay, good. All right.
I remember you saying that, but not in public.
What determines the diffusive force? Okay, good, good. Let's say that I have equal concentrations. Is there any diffusive force? Okay, good. So, if I bump this up to 70, do I have a greater difference or less of a difference in the concentration inside and out? So what happens to the diffusive force? So what do you think happens to the amount of electrical force you need to offset it? Yes, exactly. Yeah, so hopefully this is going to depolarize, but what the hell do I know? What happens when you plug 70 in there?
Negative 41.
Oh, good, it depolarized. Nice. Yeah. What do you think it would be? Don't plug anything in. If you made that 120. Nothing would change. It would stay at minus 76.
I think it's the same as X.
Go ahead and plug it in.
Oh,
Oh,
You're right, it's 0.
Oh, yeah. Now, chloride is going to be very strongly depolarizing. So, before we get out of here, just a little story about you.
okay.
Long before you were here with us. When you were, this is after you were a glimmer in your father's eye? Is that how it goes?
I wouldn't say.
Or
it's
mother's
a-
eye? Anyway, you're in the womb, okay? You're not born yet. You're still a developing you. There was a time in your life when GABA was excitatory. There was a time when GABA would get you going. And do you know why GABA would get you going? You just demonstrated it. The internal concentration of chloride was much different in your young neurons. They didn't have AMPA receptors way back when. They were naive. They had to activate their synapses. And in order to do that, they needed GABA. And GABA was excitatory because this value was not so low. You had different chloride transporters expressed. Didn't have quite the affinity for it, and so your internal chloride concentration was much higher, and as a result, the reversal was different. Now, over time, you grew up, and you're here with us today. A few things happened in between there, and one of those things that happened between then and now was that this value dropped. And that is why you no longer get as excited about gathering. But hopefully this class can change that. All right. With that, I got nothing else for you. I'll see you tomorrow.